Hello dear students, glad to meet you again in this session. In this session 2.5, we are going to discuss about Bohr's atom model from chapter 2, Structure of Atom in grade 11. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 2.1, we have discussed about the discovery of subatomic particles and its characteristics. In session 2.2, we have discussed J.J. Thomson and Rutherford atom model and its drawbacks. In session 2.3, we have discussed the dual nature of electromagnetic radiations, blackbody radiation, photoelectric effect, and electromagnetic spectrum. In session 2.4, we have discussed about continuous spectrum, emission spectrum, absorption spectrum, atomic spectrum, and line spectrum of hydrogen. Learning outcomes. Students, at the end of this session, you will be able to list the postulates of Bohr's model of hydrogen atom, explain Bohr's theory of hydrogen atom, explain the line spectrum of hydrogen, and list the limitations of Bohr's model. Niels Bohr in 1913 modified Rutherford atom model in order to overcome the limitations of Rutherford atom model. He proposed a new model of hydrogen atom based on the quantum theory of radiation. This model could explain quantitatively the general features of the structure of hydrogen atom and its spectrum. The main postulates of Bohr's atom model are the energy of the electron in an atom are quantized. According to Bohr's atom model, positively charged nucleus present at the center of the atom and the negative charge electron is revolving around the nucleus in a circular certain path of fixed energy called stationary orbits. These orbits are associated with definite energies and also called energy shells or energy level. They are numbered as 1, 2, 3, 4 and so on, or they can be named as K shell, L shell, M shell and N shell respectively. The second postulate is electron can revolve only in those orbits in which the angular momentum of the electron must be equal to the integral multiple of h by 2 pi, that is mvr is equal to nh by 2 pi, where n is the integer from 1, 2, 3 and so on and h is the Planck's constant. We know that the angular momentum of a particle moving in a circular path is equal to inertia I into angular momentum omega. We know the formula for inertia I equal to mass of the electron into radius and omega equal to velocity by radius. Substituting these values in this expression, we get angular momentum equal to m suffix e vr, where m suffix e is the mass of the electron, v is the linear velocity and r is the circular path of the radius around the nucleus. When electron remains in a particular orbit, it does not lose or gain energy. This means the energy of the electron in a particular orbit remains constant. So these orbits are called stationary states. When energy from some external source is supplied to the electron, it may jump to the higher energy level by absorbing certain amount of energy. When electron jump back to the lower energy level, it radiates the same amount of energy in the form of radiation, and this radiation is equal to the difference in the energy between the two energy level. The frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy is given by E2 minus E1 equal to h nu. We can write this expression as nu is equal to E2 minus E1 by h, where nu is the Bohr's frequency. Quantization of energy. Quantization means that a quantity cannot vary continuously to have an arbitrary values but can change only discontinuously to have some specific values. For example, consider a boy moving down a staircase. The energy of this boy changes discontinuously, and he can have only certain definite values of energy corresponding to the energies of various steps. The energy of the boy in this case is quantized. But if the same boy moves down in a slide, his energy changes continuously, and he can have any values of energy corresponding to the any point of the slide. Energy in this case is not quantized. Likewise, according to Bohr's atom model, an electron in an atom can move only in those orbits for which the angular momentum is the integral multiple of h by 2 pi. These orbits are associated with a definite amount of energy. Hence, an electron in an atom can have only certain definite values of energy. That is, the energy of an electron in an atom is quantized. According to Bohr's model for hydrogen atom, the stationary states of electron are numbered as n equal to 1, 2, 3, 4, and so on. And these integral numbers are known as principal quantum numbers. The electrostatic force between the nucleus and the electron prevents electron to fall into nucleus. Bohr's model could explain the stability of atom. Bohr was able to derive expression for the radius of an orbit in hydrogen atom. The radius of nth orbit is given by the equation Rn is equal to n square h square upon 4 pi square km e square. If we substitute the value of h Planck's constant, pi, k Coulomb's law constant, m mass of the electron, and e charge on the electron, we get the value Rn is equal to n square into 0.529 into 10 to the power of minus 10 meters. We know that 10 to the power of minus 10 meters is equal to 1 angstrom. So Rn is equal to n square into 0.529 angstrom. As the value of n increases, that is the principal quantum number increases, the radius of the orbit also increases. If we calculate the radius of the first orbit of hydrogen, that is n equal to 1, we get the value 0.529 angstrom. The value 0.529 angstrom is known as Bohr's radius, and it is expressed by the letter A suffix O. So if we substitute this value as A naught in this expression Rn, we get Rn is equal to n square into, instead of 0.529 angstrom, we can write A suffix O. On the basis of Bohr's model, it is possible to derive a mathematical relationship for energy of the electron in the nth orbit of hydrogen. It is given by the expression En is equal to minus k square into 2 pi square m e to the power of 4 upon n square h square, or we can write this expression as En is equal to minus Rh into 1 upon n square, where Rh is the Rydberg constant. If we substitute the value of m mass of the electron, E charge on the electron, H Planck's constant, K Coulomb's law constant, which is equal to 9.00 into 10 to the power of 9 joules meter per coulomb square. In this equation, we get the value of En is equal to minus 2.18 into 10 to the power of minus 18 upon n square joules per atom. Since minus 2.18 into 10 to the power of minus 18 joules is Rydberg constant, we can write the expression En is equal to minus Rh into 1 upon n square. If we express the energy of the nth orbit in terms of electron volt, then the value of En is equal to minus 13.6 upon n square. Bohr's theory can also be applied to ions containing one electron similar to that present in hydrogen atom. The energy of the electron in the nth orbit for these ions can be given by the expression En is equal to minus k square 2 pi square m e power 4 z square upon n square h square. If we substitute the value of k pi, m, e and h in this expression, we get minus 2.18 into 10 to the power of minus 18 z square upon n square joules per atom. And the radius of the nth orbit is given by the expression Rn is equal to n square h square upon 4 pi k m e square into z. If we substitute the value of h Planck's constant, pi, k Coulomb's law constant, mass of the electron and charge of the electron in this expression, we get Rn is equal to n square into 0.529 upon z angstrom. Here we can write the expression Rn is equal to n square into 52.9 upon z picometer. Z is the atomic number of the element. We know that atomic number is nothing but the number of protons present in the nucleus. Here in these ions, we could see the number of protons present in the nucleus is greater than the electron present in these ions. So it has the greater tendency to attract the electron towards itself. So obviously the radius becomes smaller with increase in the atomic number. In this problem, we are going to calculate the energy associated with the first orbit of helium plus ion and what is the radius of the orbit. First, let us calculate the energy associated with the first orbit of helium plus ion. The energy of the electron is given by the expression En equal to minus 2.18 into 10 to the power of minus 18 z square upon n square joules per atom. We know that for helium plus ion, n equal to 1 because this is the first orbit and z equal to 2. Z is nothing but the atomic number, that is the number of protons in the nucleus is 2 for helium ion, and substituting these values of n equal to 1 and z equal to 2 in the above equation, we get En is equal to minus 2.18 into 10 to the power of minus 18, 2 square upon 1 square, which gives the value minus 8.72 into 10 to the power of minus 18 joules per atom. Now let us calculate what is the radius of the orbit. The radius of the orbit is given by the expression Rn equal to n square into 0.0529 nanometer upon z. Since n equal to 1 and z equal to 2 for helium plus ion, substituting these values n equal to 1 and z equal to 2 in this above expression, we get Rn equal to 1 square into 0.0529 nanometer upon 2. If we simplify this value, we get Rn is equal to 0.02645 nanometer. It is possible to calculate the velocity of the moving electron in their orbits. Quantitatively, the magnitude of the velocity of the electron increases with increase in the positive charge on the nucleus. That is, the velocity of the electron increases with increase in the atomic number Z. Likewise, quantitatively, the magnitude of the velocity of the electron decreases with increase in the principal quantum number n. Explanation of line spectrum of hydrogen. Bohr's model explains the appearance of certain discrete lines in the spectrum of hydrogen. Bohr's model also accounts for the existence of so many lines in the hydrogen spectrum. The energy gap between two orbits is given by the equation delta E is equal to EF minus EI, where F stands for final and I stands for initial. Since we know that En is equal to minus RH Rydberg constant into 1 upon n square, we can write this expression as delta E is equal to EF minus EI, which is equal to minus RH upon NF square minus of RH upon NI square. If we multiply these two minus, it will become plus, right? So we can rewrite this equation delta E as delta E is equal to RH upon NI square minus RH upon NF square. We can take this RH as a common one, and delta E is equal to RH into 1 upon Ni square minus 1 upon Nf square. This gives the value delta E is equal to 2.18 into 10 to the power of minus 18 joules into 1 upon Ni square minus 1 upon Nf square, since RH is equal to 2.18 into 10 to the power of minus 18 joules. There is only one electron present in the first orbit, that is in the ground state level, n equal to 1 in hydrogen atom. When external energy is supplied to this electron may excite to the higher energy level. While performing experiment, we take a sample of hydrogen which contains large number of atoms. The electron in different atoms absorb different amounts of energy and are excited to different higher energy levels. For example, let us consider an electron present in the third energy level, n equal to 3, in different hydrogen atom. In some atoms, the electron may come to the ground state level by direct jump, while in some other cases, the electron may first jump to the second energy level and then to the first energy level. These different downward jumps emit different amount of energies and hence result in the emission of radiations of different wavelengths, which appear as different lines in the hydrogen spectrum. Large number of different types of downward direction takes place simultaneously in a sample of hydrogen. Therefore, large number of lines are obtained in the emission spectrum of hydrogen. The lines appear due to the transition of electrons from the higher energy level to the first level, second level, third level, fourth level, and fifth level are named as Lyman series belongs to ultraviolet region, Balmer series belongs to visible region, Paschal, bracket, and Fun series belongs to infrared regions. In this problem, we are going to calculate the frequency nu associated with the absorption and emission of photon, and it can be evaluated by using the equation nu is equal to delta E upon H. We can substitute delta E as RH, Rydberg constant, into 1 upon Ni square minus 1 upon Nf square, and H is equal to 6.626 into 10 to the power of minus 34 joule second, which is the Planck's constant. If we substitute delta E and H in the expression nu is equal to delta E upon H, we get nu is equal to 2.18 into 10 to the power of minus 18 joules upon 6.626 into 10 to the power of minus 34 joules second into 1 upon Ni square minus 1 upon Nf square. We can cross this joules in the numerator and in the denominator. Now the unit will become second inverse. We can write the second inverse as Hertz. If we simplify these two values, we get nu is equal to 3.29 into 10 to the power of 15 into 1 upon Ni square minus 1 upon Nf square Hertz. Now we can calculate the wave number nu bar associated with the absorption and emission of photon, and it can be evaluated by using the expression nu bar is equal to nu upon C. We can write nu as RH, Rydberg constant, upon H, Planck's constant, into 1 upon Ni square minus 1 upon Nf square. Just now we have calculated the value of nu as 3.29 into 10 to the power of 15 per second into 1 upon Ni square minus 1 upon Nf square, and the value of C, the speed of light, is equal to 3 into 10 to the power of 8 meter per second. If we substitute the value of nu and C in the equation nu bar equal to nu by C, we get nu bar equal to 3.29 into 10 to the power of 15 per second upon 3 into 10 to the power of 8 meter per second into 1 upon Ni square minus 1 upon Nf square. We can cross this second inverse in the numerator and in the denominator. If we simplify this value, we get 1.09677 into 10 to the power of 7 into 1 upon Ni square minus 1 upon Nf square. This meter from the denominator comes to the numerator, it will become m to the power of minus 1. If Nf is greater than Ni, the term in the parenthesis is positive and it indicates the energy is absorbed. If Ni is greater than Nf, the term in the parenthesis is negative and this indicates the energy is released. Limitations of Bohr's model. It fails to account for the finer details, that is, too closely spaced lines of the hydrogen atom spectrum observed by using sophisticated techniques, and it could not explain the splitting of spectral lines in the presence of magnetic field, that is the Zeeman effect, and the splitting of spectral lines under the effect of applied electric field, that is Stark effect. Moreover, it could not explain the ability of atoms to form molecules and the geometry and the shapes of molecule. Bohr has treated electron only as particle and ignored the dual character of electron suggested by de Broglie, the French physicist. According to Heisenberg's uncertainty principle, it is impossible to determine simultaneously the momentum and the exact position of a small moving particle like an electron. Bohr postulates that the electron move in a well-defined orbits around the nucleus. In this way, Bohr's model contradicts Heisenberg's uncertainty principle. Students, now let's recall all the topics that we have discussed in this session. We have discussed the postulates of Bohr's model for hydrogen atom, and explanation about Bohr's model for hydrogen atom, and the explanation about the line spectra of hydrogen and limitations of Bohr's model. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.